It is only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the atom. It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously. The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, a carbon nucleus can eject a fast-moving electron and turn into a nitrogen nucleus. There are two different particles that can be emitted from radioactive nuclei, though never together. The very fast electron is known as a beta particle. If you know a little bit about electrons, you may be thinking, what was the electron doing in the nucleus in the first place? The answer is that a neutron in the nucleus spontaneously changed into a proton, which stayed behind, and an electron flew out as a beta particle. This is not what chemistry has taught us to expect. The nucleus is supposed to be stable. Neutrons don't change into protons, except sometimes they do. The other particle that emits spontaneously from an unstable nucleus is alpha. An alpha particle is 8,000 times more massive than beta, and it's a bit slower. Alpha is made from 2 protons and 2 neutrons. If we trap a lot of alpha particles together, we get helium gas. Alpha is a helium nucleus. Like the beta particle, we would not have expected a heavier nucleus to throw out helium. But again, it happens, and the nucleus becomes a new element. So, is radioactivity useful or just dangerous? Wherever you are sitting, it is quite likely that there is a device nearby which contains a source of alpha particles, a smoke detector. The source is radioactive americium. You are totally safe from these alpha particles, which cannot travel more than a few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers, to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic than visible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit to increase its shelf life, or in radiotherapy to kill cancer cells. Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. Alpha causes the most ionization as it crashes into other atoms, and gamma the least. For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly, but it is all around us as a background to the natural world.
Olive oil is 100% fat. There's nothing else in it. Pancake mix, on the other hand, is only about 11% fat. And yet, olive oil is good for you, and pancake mix is not. Why is that? As it turns out, the amount of fat we eat doesn't impact our weight or our cholesterol or our risk of heart disease nearly as much as what kind of fat we eat. But let's back up. What is fat? If we were to zoom in on a salmon, which is a fatty fish, past the organs, past the tissues, into the cells, we would see that the stuff we call fat is actually made up of molecules called triglycerides, and they are not all alike. Here's one example. Those 3 carbons on the left, that's glycerol. Now you can think of that as the backbone that holds the rest of the molecule together. The 3 long chains on the right are called fatty acids, and it's subtle differences in the structures of these chains that determine whether a fat is, let's say, solid or liquid, whether or not it goes rancid quickly, and, most importantly, how good or how bad it is for you. Let's take a look at some of these differences. One is length. Fatty acids can be short or long. Another, more important difference is the type of bond between the carbon atoms. Some fatty acids have only single bonds. Others have both single and double bonds. Fatty acids with only single bonds are called saturated, and those with one or more double bonds are called unsaturated. Now, most unsaturated fats are good for you, while saturated fats are bad for you in excess. For saturated fats, the story pretty much ends there, but not for unsaturated fats. The double bonds in these molecules have kind of a weird property. They're rigid. So that means that there are 2 ways to arrange every double bond. The first is like this, where both hydrogens are on the same side and both carbons are on the same side. The second way is like this. Now the hydrogens and carbons are on opposite sides of the double bond. Now, even though both of these molecules are made up of exactly the same building blocks, they are 2 completely different substances and they behave completely differently inside of us. The configuration on the left is called cis, which you've probably never heard of. The one on the right is called trans, and you probably have heard of trans fats before. They don't go rancid, they're more stable during deep frying, and they can change the texture of foods in ways that other fats just can't. They're also terrible for your health, by far worse than saturated fat, even though technically they're a type of unsaturated fat. Now, I know that seems crazy, but your body doesn't care what a molecule looks like on paper. All that matters is the 3D shape, where the molecule fits, where it doesn't, and what pathways it interferes with. So how do you know if a food has trans fat in it? Well, the only sure way to know is if you see the words partially hydrogenated in the ingredients list. Don't let nutrition labels or advertising fool you. The FDA allows manufacturers to claim that their products contain, quote, 0 grams of trans fat, even if they actually have up to half a gram per serving. But there are no hard and fast rules about how small a serving can be, and that means you'll have to rely on seeing those key words, partially hydrogenated, because that's how trans fats are made, by partially hydrogenating unsaturated fats. So let's go back to our olive oil and pancake mix from before. Olive oil is 100% fat. Pancake mix is only 11% fat. But olive oil is mostly unsaturated fat, and it has no trans fat at all. On the other hand, more than half the fat in pancake mix is either saturated or trans fat. And so even though olive oil has 10 times as much fat as pancake mix, it's healthy for you, whereas pancake mix is not. Now, I'm not trying to pick on pancake mix. There are lots of foods with this type of fat profile. The point is this. It's not how much fat you eat, it's what kind of fat. And what makes a particular fat healthy or unhealthy is its shape.
Nowadays, we take curiosity for granted. We believe that if we put in the hard work, we might one day stand before the pyramids, discover a new species of flower, or even go to the moon. But in the 18th and 19th century, female eyes gazed out windows at a world they were unlikely to ever explore. Life for women in the time of Queen Victoria was largely relegated to house chores and gossip, and although they devoured books on exotic travel, most would never leave the places in which they were born. However, there were a few Victorian women who, through privilege, endurance, and not taking no for an answer, did set sail for wilder shores. In 1860, Mary Ann North, an amateur gardener and painter, crossed the ocean to America with letters of introduction, an easel, and a love of flowers. She went on to travel to Jamaica, Peru, Japan, India, Australia. In fact, she went to every continent except Antarctica in pursuit of new flowers to paint. I was overwhelmed with the amount of subjects to be painted, she wrote. The hills were marvelously blue, piled one over the other beyond them. I never saw such abundance of pure color. With no planes or automobiles and rarely a paved street, North rode donkeys, scaled cliffs, and crossed swamps to reach the plants she wanted. and all this in the customary dress of her day, floor-length gowns. As photography had not yet been perfected, Marianne's paintings gave botanists back in Europe their first glimpses of some of the world's most unusual plants, like the giant pitcher plant of Borneo, the African torch lily, and the many other species named for her, as she was the first European to catalogue them in the wild. Meanwhile, back in London, Miss Mary Kingsley was the sheltered daughter of a travelling doctor who loved hearing her father's tales of native customs in Africa. Midway through writing a book on the subject, her father fell ill and died, so Kingsley decided she would finish the book for him. Peers of her father advised her not to go, showing her maps of tropical diseases, but she went anyhow, landing in modern-day Sierra Leone in 1896 with 2 large suitcases and a phrase book. Traveling into the jungle, she was able to confirm the existence of a then mythical creature, the gorilla. She recalls fighting with crocodiles, being caught in a tornado, and tickling a hippopotamus with her umbrella so that he'd leave the side of her canoe. Falling into a spiky pit, she was saved from harm by her thick petticoat. "A good snake, properly cooked, is one of the best meals one gets out here," she wrote. Think Indiana Jones was resourceful? Kingsley could out-survive him any day. But when it comes to breaking rules, perhaps no female traveler was as daring as Alexandra David Neal. Alexandra, who had studied Eastern religions at home in France, wanted desperately to prove herself to Parisian scholars of the day, all of whom were men. She decided the only way to be taken seriously was to visit the fabled city of Lhasa in the mountains of Tibet. "People will have to say, 'This woman lived among the things she's talking about. She touched them, and she saw them alive,'" she wrote. When she arrived at the border from India, she was forbidden to cross, so she disguised herself as a Tibetan man. Dressed in a yak fur coat and a necklace of carved skulls, she hiked through the barren Himalayas all the way to Lhasa, where she was subsequently arrested. She learned that the harder the journey, the better the story, and went on to write many books on Tibetan religion, which not only made a splash back in Paris, but remain important today. These brave women, and others like them, went all over the world to prove that the desire to see for oneself not only changes the course of human knowledge, it changes the very idea of what is possible. They used the power of curiosity to try and understand the viewpoints and peculiarities of other places, perhaps because they themselves were seen as so unusual in their own societies. But their journeys revealed to them something more than the ways of foreign lands. They revealed something only they themselves could find, a sense of their own self.
We talk about inventions and innovation as though the best things out there are the internet, iPads, or smartphones, or perhaps more simply, trains, planes, and automobiles. Which one is the most important? The best or the greatest? Which one has had the most impact on society? Today, the debate would probably be in favor of computer technology. But is it? Well, some would say, nope, not really, it's farming. Where would we be if we didn't have it? Give up? We would still be hunting and gathering with little time to invent anything, let alone the internet. That's right, farming is the seed of civilization. Not quite literally, but without early man's discovery of using seeds to grow grain, we wouldn't have much of anything we have today. Growing your own food changed everything. Sure, hunting and gathering worked just fine for tens of thousands of years, but you couldn't do much else. No time. But when hunters and gatherers started planting seeds, they began to farm. With farming came animals, and with animals came settling down and staying in one location. So how does this have anything to do with invention and innovation? Everything. Anyone who's ever farmed, even if it's planting a half-dozen tomato plants in your backyard, knows that you usually harvest way more than you could possibly eat. A surplus. Farming yielded plenty of food, with enough to store, trade, and eat. In other words, not everyone needed to be farmers. Therefore, this allowed other people, non-farmers, to do other things, such as make tools, craft pottery, and build homes. Farming and food surpluses led to the division of labor. This is still thousands of years ago, so life wasn't easy. But with so many people contributing to the community, small villages began to develop. As the population of villages expanded, so did the needs of the people. Things got complicated. But civilization is just that, advanced, complex societies. And without farming, they would not exist. Villages increased in size, eventually becoming the first cities. Cities are just one of the basic features of a civilization. The others include central government, system of writing, organized religion, art and architecture, urban planning of roads, bridges, and public works, social classes, and different jobs. Developing expertise in various types of occupations allowed for innovative ways of doing things, producing new products, or making advancements in technology. As civilizations became more complex, new ways of doing things were needed. Some were out of necessity, others because people had ideas. The sharing of ideas and technology led to the growth of things we readily use today, like the internet. So without farming, we'd still be hunting and gathering, no video, no computers, and certainly no World Wide Web.
How big was that fish you caught? This big? This big? This big? Without photographic evidence, there's nothing that proves you caught a whopper. And that's been true since the dawn of fishing. In fact, hundreds of years ago, long before photography could capture the moment, Japanese fishermen invented their own way to record trophy catches. They called it gyotaku. Gyotaku is the ancient art of printing fish that originated in Japan as a way to record trophy catches prior to the modern-day camera. Gyo means fish, and taku means impression. There are several different stories about how gyotaku came about, but it basically started with fishermen needing a way to record the species and size of the fish they caught over 100 years ago. Fishermen took paper, ink, and brushes out to sea with them. They told stories of great adventures at sea. Since the Japanese revered certain fish, the fishermen would take a rubbing from these fish and release them. To make the rubbing, they would paint the fish with non-toxic sumi ink and print them on rice paper. This way, they could be released or cleaned and sold at market. The first prints like this were for records only, with no extra details. It wasn't until the mid-1800s that they began painting eye details and other embellishments onto the prints. One famous nobleman, Lord Sakai, was an avid fisherman, and when he made a large catch, he wanted to preserve the memory of the large red sea bream. To do so, he commissioned a fisherman to print his catch. After this, many fishermen would bring their gyotaku prints to Lord Sakai, and if he liked their work, he would hire them to print for him. Many prints hung in the palace during the Edo period. After this period, gyotaku was not as popular and began to fade away. Today, gyotaku has become a popular art form enjoyed by many, and the prints are said to bring good luck to the fishermen, but the art form is quite different than it used to be. Most artists today learn on their own by trial and error. Before the artist begins to print, the fish needs to be prepared for printing. First, the artist places the fish on a hollowed-out surface. Then the artist spreads the fins out and pins them down on the board to dry. They then clean the fish with water. When it comes time to print, there are two different methods. The indirect method begins with pasting moist fabric or paper onto the fish using rice paste. Then the artist uses a tampo or a cotton ball covered in silk to put ink on the fabric or paper to produce the print. This method requires more skill, and great care needs to be taken when pulling the paper off the fish so the paper doesn't tear. In the direct method, the artist paints directly on the fish and then gently presses the moist fabric or paper into the fish. With both of these methods, no two prints are exactly alike, but both reveal dramatic images of the fish. For the final touch, the artist uses a chop or stamp and signs their work, and can hold it up to say the fish was exactly this big.
Feathers are some of the most remarkable things ever made by an animal. They are gorgeous in their complexity, delicate in their construction, and yet strong enough to hold a bird thousands of feet in the air. Like all things in nature, feathers evolved over millions of years into their modern form. It can be hard to imagine how this could have happened. After all, what did the intermediate forms look like? What good is half a wing, festooned with half feathers? Thanks to science, we now know that birds are living dinosaurs. You can see the kinship in their skeletons. Certain dinosaurs share some anatomical details with birds found in no other animals, such as wishbones. And in the late 1990s, paleontologists started digging up some compelling support for that idea. Dinosaurs with bits of feathers still preserved on their bodies. Since then, scientists have found dozens of species of dinosaurs with remnants of feathers. Some were as small as pigeons, and some were the size of a school bus. If you look at how they're related on a family tree, the evolution of feathers doesn't seem quite so impossible. The most distant feathered relatives of birds had straight feathers that looked like wires. Then these wires split apart, producing simple branches. In many dinosaur lineages, these simple feathers evolved into more intricate ones, including some that we see today on birds. At the same time, the feathers spread across the bodies of dinosaurs, turning from sparse patches of fuzz into dense plumage, which even extended down to their legs. A few fossils even preserve some of the molecules that give feathers color. They reveal a beautiful range of colors: glossy dark plumage, reminiscent of crows, alternating stripes of black and white, or splashes of bright red. Some dinosaurs had high crests on their heads, and others had long, dramatic tail feathers. Now, none of these dinosaurs could use their feathers to fly. Their arms were too short, and the rest of their bodies were far too heavy. But birds don't just use feathers to fly. A woodcock uses feathers to blend in perfectly with its forest backdrop. An ostrich stretches its wings over its nest to shade its young. A peacock displays its magnificent tail feathers to attract peahens. Feathers could have served these functions for dinosaurs too. Exactly how feathered dinosaurs took flight is still a bit of a mystery. But if a small feathered dinosaur flapped its arms as it ran up an incline, its feathers would have provided extra lift to help it run faster. This accident of physics might have led to the evolution of longer dinosaur arms, which would let them run faster and even leap short distances through the air. Eventually, their arms stretched out into wings. Only then, perhaps 50 million years after the first wiry feathers evolved, did feathers lift those dinosaurs into the sky.
What lights up the screen that you're looking at right now? Trace back the battery chargers and power cords, and you'll end up at an electrical outlet, providing easy, safe access to reliable electricity. But beyond that outlet, the picture gets messier. It takes a lot of fuel to heat our homes, preserve our food, and power our gadgets around the clock. And for 40% of the world, that fuel is cheap, plentiful, and it's called coal. But coal also releases pollutants into the air, like sulfur dioxide, nitrogen oxides, soot, and toxic metals like mercury. These cause environmental damage like acid rain and serious health problems. In fact, in 1952, coal burning caused such heavy smog in London that pedestrians couldn't even see their feet, and thousands of people died from ill health. Since then, many countries have deployed technology to remove most of these pollutants before they reach the air. But now we have a new air pollution problem on our hands, one that doesn't show up in a cloud of dark smog, but in rising seas, floods, and heat waves. It's global climate change. And again, the main culprit is coal. It's responsible for 44% of global carbon dioxide emissions, which trap the sun's heat in the Earth's atmosphere instead of letting it escape. So now the question is, how do we remove that bad stuff as well? That's the idea behind cleaner coal. Creating cleaner coal is really about trying to contain its ill effects with the help of special technologies that make the end product more acceptable. Just like the most intriguing superheroes often have their own dark powers to overcome, so we can try and keep coal's negative forces in check. But why don't we just exterminate coal if it takes that much effort to clean it up? Simply, coal is extremely valuable to us, and it's easy to come by. Compressed underground for ages, coal holds chemical energy from plants that were fed by the sun hundreds of millions of years ago, long before humans evolved. That makes coal energy dense, meaning it can be burned round the clock. It's also cheap if you ignore the pollution costs, and should last us through the end of the 21st century. We've already got all the infrastructure in place for harnessing its power. And globally, although countries are making a move towards energy from cleaner and more renewable sources, there's no sign yet that coal use is slowing down. In fact, as of 2012, over 1,000 new coal plants have been proposed, mostly in China and India. Since, for the time being, coal is here to stay, experts say that if we want to reduce its emissions impact on the atmosphere and slow down climate change, we'll have to think of creative ways of reducing coal's destructive power. To do that, we need to strip it of its foul forces, all that toxic carbon dioxide that causes havoc in the atmosphere. Then we need to store this CO2 somewhere else. This mission is called Carbon Capture and Sequestration, or CCS. And as if carbon dioxide were some evil genie we didn't want to escape, once it has been separated from coal, we've devised ways to banish it underground. We can do this by injecting it deep into the earth or by placing it deep under the ocean's surface. Stripping away coal's negative elements can happen in three ways. First, and most commonly, as coal burns, the exhaust gas can be mixed with a compound called monoethanolamine. Like a forceful power-stripping magnet, this compound bonds to the CO2, yanking it out of the gas stream so it can be stored separately underground. Another method is to relieve coal of its CO2 before it even has a chance to be released as exhaust. In this process, steam and oxygen swoop in to the rescue to convert coal into a special product called syngas, made up of carbon monoxide and hydrogen and some CO2. Zap that with some water vapor, and the carbon monoxide gets converted into carbon dioxide, which can be isolated. The leftover hydrogen gas is then used as energy to generate electricity, so there's an added bonus. A third technique exposes coal to pure oxygen instead of burning it in air. This creates exhaust gas with higher concentrations of carbon dioxide, which makes it easy to isolate and to banish to the chasms below. All this can reduce emissions at a power plant by up to 90%. But as with any superhero struggling with their destructive powers, it takes a lot of effort to switch over from the dark side. So these positive pollution-busting forces, although they're available, have barely been used in commercial power plants because they cost a lot. But ultimately, the bigger problem is that in most parts of the world, it's still too easy and much cheaper to keep emitting carbon dioxide. And that makes it tempting to completely ignore coal's dark side. In this case, the most powerful force for good is regulation, the rules that can restrict the amount of carbon dioxide emitted from power plants and make energy companies around the world wary of what they put into the air. Until then, every time you turn on a screen or flick a light switch, coal is lurking in the background, carrying its dark powers with it wherever it goes.
been many different things written and said about marriage, from the sweetly inspirational to the hilariously cynical. But what many of them have in common is that they sound like they express a universal and timeless truth, when in fact, nearly everything about marriage, from its main purpose to the kinds of relationships it covers to the rights and responsibilities involved, has varied greatly between different eras, cultures, and social classes. So let's take a quick look at the evolution of marriage. Pair bonding and raising children is as old as humanity itself. With the rise of sedentary agricultural societies about 10,000 years ago, marriage was also a way of securing rights to land and property by designating children born under certain circumstances as rightful heirs. As these societies became larger and more complex, marriage became not just a matter between individuals and families, but also an official institution governed by religious and civil authorities. And it was already well established by 2100 BC, when the earliest surviving written laws in the Mesopotamian Code of Ur-Nammu provided many specifics governing marriage, from punishments for adultery to the legal status of children born to slaves. Many ancient civilizations allowed some form of multiple simultaneous marriage, and even today, less than a quarter of the world's hundreds of different cultures prohibit it. But just because something was allowed doesn't mean it was always possible. Demographic realities, as well as the link between marriage and wealth, meant that even though rulers and elites in ancient Mesopotamia, Egypt, and Israel had multiple concubines or wives, most commoners could only afford one or two, tending towards monogamy in practice. In other places, the tables were turned, and a woman could have multiple husbands, as in the Himalayan mountains, where all brothers in a family marrying the same woman kept the small amount of fertile land from being constantly divided into new households. Marriages could vary not only in the number of people they involved, but the types of people as well. Although the names and laws for such arrangements may have differed, publicly recognized same-sex unions have popped up in various civilizations throughout history. Mesopotamian prayers included blessings for such couples, while Native American two-spirit individuals had relationships with both sexes. The first instances of such arrangements actually being called marriage come from Rome, where the emperors Nero and Elagabalus both married men in public ceremonies, with the practice being explicitly banned in 342 AD. But similar traditions survived well into the Christian era, such as adelphopoiesis or brother-making in Orthodox churches, and even an actual marriage between two men recorded in 1061 at a small chapel in Spain. Nor was marriage even necessarily between two living people. Ghost marriages, where either the bride or groom were deceased, were conducted in China to continue family lineages or appease restless spirits, and some tribes in Sudan maintained similar practices. Despite all these differences, a lot of marriages throughout history did have one thing in common. With crucial matters like property and reproduction at stake, they were way too important to depend on young love. Especially among the upper classes, matches were often made by families or rulers. But even for commoners who had some degree of choice, the main concern was practicality. The modern idea of marriage as being mainly about love and companionship only emerged in the last couple of centuries. With industrialization, urbanization, and the growth of the middle class, more people became independent from large extended families and were able to support a new household on their own. Encouraged by new ideas from the Enlightenment, people began to focus on individual happiness and pursuits rather than familial duty or wealth and status, at least some of the time. And this focus on individual happiness soon led to other transformations, such as easing restrictions on divorce and more people marrying at a later age. So as we continue to debate the role and definition of marriage in the modern world, it might help to keep in mind that marriage has always been shaped by society, and as a society's structure, values, and goals change over time, its ideas of marriage will continue to change along with them.
One of the most amazing facts in physics is this. Everything in the universe, from light to electrons to atoms, behaves like both a particle and a wave at the same time. All of the other weird stuff you might have heard about quantum physics, Schrödinger's cat, God playing dice, spooky action at a distance, all of it follows directly from the fact that everything has both particle and wave nature. This might sound crazy. If you look around, you'll see waves in water and particles of rock, and they're nothing alike. So why would you think to combine them? Physicists didn't just decide to mash these things together out of nowhere. Rather, they were led to the dual nature of the universe through a process of small steps, fitting together lots of bits of evidence, like pieces in a puzzle. The first person to seriously suggest the dual nature of light was Albert Einstein in 1905. But he was picking up an earlier idea from Max Planck. Planck explained the colors of light emitted by hot objects, like the filament in a light bulb. But to do it, he needed a desperate trick. He said the object was made up of oscillators that could only emit light in discrete chunks, units of energy that depend on the frequency of the light. Planck was never really happy with this, but Einstein picked it up and ran with it. He applied Planck's idea to light itself, saying that light, which everybody knew was a wave, is really a stream of photons, each with a discrete amount of energy. Einstein himself called this the only truly revolutionary thing he did, but it explains the way light shining on a metal surface knocks loose electrons. Even people who hated the idea had to agree that it works brilliantly. The next puzzle piece came from Ernest Rutherford in England. In 1909, Ernest Marsden and Hans Geiger, working for Rutherford, shot alpha particles at gold atoms and were stunned to find that some bounced straight backwards. This showed that most of the mass of the atom is concentrated in a tiny nucleus. The cartoon atom you learn in grade school, with electrons orbiting like a miniature solar system, that's Rutherford's. There's one little problem with Rutherford's atom. It can't work. Classical physics tells us that an electron whipping around in a circle emits light, and we use this all the time to generate radio waves and X-rays. Rutherford's atom should spray X-rays in all directions for a brief instant before the electron spirals in to crash into the nucleus. But Niels Bohr, a Danish theoretical physicist working with Rutherford, pointed out that atoms obviously exist, so maybe the rules of physics needed to change. Bohr proposed that an electron in certain special orbits doesn't emit any light at all. Atoms absorb and emit light only when electrons change orbits, and the frequency of the light depends on the energy difference in just the way Planck and Einstein introduced. Bohr's atom fixes Rutherford's problem and explains why atoms emit only very specific colors of light. Each element has its own special orbits, and thus its own unique set of frequencies. The Bohr model has one tiny problem. There's no reason for those orbits to be special. But Louis de Broglie, a French PhD student, brought everything full circle. He pointed out that if light, which everyone knew is a wave, behaves like a particle, maybe the electron, which everyone knew is a particle, behaves like a wave. And if electrons are waves, it's easy to explain Bohr's rule for picking out the special orbits. Once you have the idea that electrons behave like waves, you can go look for it. And within a few years, scientists in the US and UK had observed wave behavior from electrons. These days, we have a wonderfully clear demonstration of this, shooting single electrons at a barrier with slits cut in it. Each electron is detected at a specific place at a specific time, like a particle. But when you repeat the experiment many times, all the individual electrons trace out a pattern of stripes, characteristic of wave behavior. The idea that particles behave like waves and vice versa is one of the strangest and most powerful in physics. Richard Feynman famously said that this illustrates the central mystery of quantum mechanics. Everything else follows from this, like pieces of a puzzle falling into place.
If someone asked you who the richest people in history were, who would you name? Perhaps a billionaire banker or corporate mogul like Bill Gates or John D. Rockefeller. How about African King Musa Kita I? Ruling the Mali Empire in the 14th century CE, Mansa Musa, or the King of Kings, amassed a fortune that possibly made him one of the wealthiest people who ever lived. But his vast wealth was only one piece of his rich legacy. When Mansa Musa came to power in 1312, much of Europe was racked by famine and civil wars. But many African kingdoms and the Islamic world were flourishing, and Mansa Musa played a great role in bringing the fruits of this flourishing to his own realm. By strategically annexing the city of Timbuktu and re-establishing power over the city of Galle, he gained control over important trade routes between the Mediterranean and the West African coast, continuing a period of expansion which dramatically increased Mali's size. The territory of the Mali Empire was rich in natural resources, such as gold and salt. The world first witnessed the extent of Mansa Musa's wealth in 1324, when he took his pilgrimage to Mecca. Not one to travel on a budget, he brought a caravan stretching as far as the eye could see. Accounts of this journey are mostly based on an oral testimony and differing written records, so it's difficult to determine the exact details. But what most agree on is the extravagant scale of the excursion. Chroniclers describe an entourage of tens of thousands of soldiers, civilians, and slaves, 500 heralds, bearing gold staffs and dressed in fine silks, and many camels and horses bearing an abundance of gold bars. Stopping in cities such as Cairo, Mansa Musa is said to have spent massive quantities of gold, giving to the poor, buying souvenirs, and even having mosques built along the way. In fact, his spending may have destabilized the regional economy, causing mass inflation. This journey reportedly took over a year, and by the time Mansa Musa returned, tales of his amazing wealth had spread to the ports of the Mediterranean. Mali and its king were elevated to near legendary status, cemented by their inclusion on the 1375 Catalan Atlas. One of the most important world maps of medieval Europe, it depicted the king holding a scepter and a gleaming gold nugget. Mansa Musa had literally put his empire and himself on the map. But material riches weren't the king's only concern. As a devout Muslim, he took a particular interest in Timbuktu, already a center of religion and learning prior to its annexation. Upon returning from his pilgrimage, he had the great Djinguereber Mosque built there with the help of an Andalusian architect. He also established a major university, further elevating the city's reputation and attracting scholars and students from all over the Islamic world. Under Mansa Musa, the empire became urbanized, with schools and mosques in hundreds of densely populated towns. The king's rich legacy persisted for generations, and to this day, there are mausoleums, libraries, and mosques that stand as a testament to this golden age of Mali's history.
One of the most striking properties about light is that it has color. To understand the phenomenon of color, it helps to think about light as a wave. But before we get to that, let's talk a little bit about waves in general. Imagine you're sitting on a boat on the ocean, watching a cork bob up and down in the water. The first thing you notice about the motion is that it repeats itself. The cork traces the same path over and over again, up and down, up and down. This repetitive, or periodic, motion is characteristic of waves. Then you notice something else. Using a stopwatch, you measure the time it takes for the piece of cork to go from its highest position down to its lowest and then back up again. Suppose this takes 2 seconds. To use the physics jargon, you've measured the period of the waves that the cork is bobbing on. That is, how long it takes a wave to go through its full range of motion once. The same information can be expressed in a different way by calculating the wave's frequency. Frequency, as the name suggests, tells you how frequent the waves are. That is, how many of them go by in 1 second. If you know how many seconds one full wave takes, then it's easy to work out how many waves go by in 1 second. In this case, since each wave takes 2 seconds, the frequency is 0.5 waves per second. So, enough about bobbing corks. What about light and colour? If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called colour. That's right, colour is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its colour, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of colour called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colours of light, so light of all colours is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colours. What happens to the blue, purple and red light? They get absorbed, and the energy they are carrying gets turned into heat. It's similar with objects of other colours. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colours of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favourite Metallica t-shirt on a sunny day.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty! Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus, how dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
The 5 Fingers of Evolution. A thorough understanding of biology requires a thorough understanding of the process of evolution. Most people are familiar with the process of natural selection. However, this is just one of 5 processes that can result in evolution. Before we discuss all 5 of these processes, we should define evolution. Evolution is simply change in the gene pool over time. But what is a gene pool? And, for that matter, what is a gene? Before spending any more time on genetics, let us begin with a story. Imagine that a boat capsizes and 10 survivors swim to shore on a deserted island. They are never rescued and they form a new population that exists for thousands of years. Strangely enough, 5 of the survivors have red hair. Red hair is created when a person inherits 2 copies of the red gene from their parents. If you only have 1 copy of the gene, you won't have red hair. To make this easier, we will assume that the 5 non-redheads are not carriers of the gene. The initial frequency of the red hair gene is therefore 50%, or 10 of 20 total genes. These genes are the gene pool. The 20 different genes are like cards in a deck that keep getting reshuffled with each new generation. Sex is simply a reshuffling of the genetic deck. The cards are reshuffled and passed to the next generation. The deck remains the same, 50% red. The genes are reshuffled and passed to the next generation. The gene pool remains the same, 50% red. Even though the population may grow in size over time, the frequency should stay at about 50%. If this frequency ever varies, then evolution has occurred. Evolution is simply change in the gene pool over time. Think about it in terms of the cards. If the frequency of the cards in the deck ever changes, evolution has occurred. There are 5 processes that can cause the frequency to change. To remember these processes, we will use the fingers on your hand, starting from the little finger and moving to the thumb. The little finger should remind you that the population can shrink. If the population shrinks, then chance can take over. For example, if only 4 individuals survive an epidemic, then their genes will represent the new gene pool. The next finger is the ring finger. This finger should remind you of mating because a ring represents a couple. If individuals choose a mate based on their appearance or location, the frequency may change. If red-headed individuals only mate with red-headed individuals, they could eventually form a new population.
If no one ever mates with red-headed individuals, these genes could decrease. The next finger is the middle finger. The M in the middle finger should remind you of the M in the word mutation. If a new gene is added through mutation, it can affect the frequency. Imagine a gene mutation creates a new color of hair. This would obviously change the frequency in the gene pool. The pointer finger should remind you of movement. If new individuals flow into an area or immigrate, the frequency will change. If individuals flow out of an area or emigrate, then the frequency will change. In science, we refer to this movement as gene flow. All four of the processes represented by our fingers can cause evolution: small population size, non-random mating, mutations, and gene flow. However, none of them lead to adaptation. Natural selection is the only process that creates organisms better adapted to their local environment. I use the thumb to remember this process. Nature votes thumbs up for adaptations that will do well in their environment and thumbs down to adaptations that will do poorly. The genes for individuals that are not adapted for their environment will gradually be replaced by those that are better adapted. Red hair is an example of one of these adaptations. Red hair is an advantage in the northern climates because the fair-skinned allowed ancestors to absorb more light and synthesize more vitamin D. Thumbs up. However, this was a disadvantage in the more southern climates where increased UV radiation led to cancer and decreased fertility. Thumbs down. Even the thumb itself is an adaptation form through the process of natural selection. The evolution that we have described is referred to as microevolution because it refers to a small change. However, this form of evolution may eventually lead to macroevolution or speciation. Every organism on the planet shares ancestry with a single common ancestor. All living organisms on the planet are connected back in time through the process of evolution. Take a look at your own hand. It's an engineering masterpiece that was created by the 5 processes I just described over millions and millions of years. Can you recall the 5 main causes of evolution from memory? If you can't, hit rewind and watch that part again. But if you can, give yourself or your neighbor a big 5-fingered high five.
On a typical day at school, endless hours are spent learning the answers to questions. But right now, we'll do the opposite. We're going to focus on questions where you can't learn the answers because they're unknown. I used to puzzle about a lot of things as a boy. For example, what would it feel like to be a dog? Do fish feel pain? Well, how about insects? Was the Big Bang just an accident? I mean, is there a God? And if so, how are we so sure that it's a he and not a she? And why do so many innocent people and animals suffer terrible things? Is there really a plan for my life? Is the future yet to be written? Or is it already written and we just can't see it? But then, do I have free will? I mean, who am I anyway? Am I just a biological machine? But then, why am I conscious? What is consciousness? Will robots become conscious one day? I mean, I kind of assumed that someday I would be told the answers to all these questions. I mean, someone must know, right? Guess what? No one knows. Most of those questions puzzle me more now than ever. But diving into them is exciting because it takes you to the edge of knowledge and you never know what you'll find there. So, 2 questions to kick off this series. Questions that no one on Earth knows the answer to.
the funny things about owning a brain is that you have no control over the things that it gathers and holds on to, the facts and the stories. And as you get older, it only gets worse. Things stick around for years sometimes before you understand why you're interested in them, before you understand their import to you. Here's 3 of mine. When Richard Feynman was a young boy in Queens, he went for a walk with his dad and his wagon and a ball. And he noticed that when he pulled the wagon, the ball went to the back of the wagon. And he asked his dad, why does the ball go to the back of the wagon? And his dad said, that's inertia. He said, what's inertia? And his dad said, inertia is the name that scientists give to the phenomenon of the ball going to the back of the wagon. But in truth, nobody really knows. Feynman went on to earn degrees at MIT, Princeton. He solved the Challenger disaster. He ended up winning the Nobel Prize in physics for his Feynman diagrams describing the movement of subatomic particles. And he credits that conversation with his father as giving him a sense that the simplest questions could carry you out to the edge of human knowledge, and that's where he wanted to play. And play he did. Now, Eratosthenes was the 3rd librarian at the Great Library at Alexandria, and he made many contributions to science. But the one he is most remembered for began in a letter that he received as the librarian from the town of Swenet, which was south of Alexandria. The letter included this fact that stuck in Eratosthenes' mind, and the fact was that the writer said at noon, on the solstice, when he looked down this deep well, he could see his reflection at the bottom, and he could also see that his head was blocking the sun. Now, I should tell you, the idea that Christopher Columbus discovered that the world is spherical is total bull. It's not true at all. In fact, everyone who was educated understood that the world was spherical since Aristotle's time, and Aristotle had proved it with a simple observation. He noticed that every time you saw the Earth's shadow on the moon, it was circular. And the only shape that constantly creates a circular shadow is a sphere, QED. The Earth is round. But nobody knew how big it was until Eratosthenes got this letter with this fact. So he understood that the sun was directly above the city of Swenet, because looking down a well, it was a straight line all the way down the well, right past the guy's head up to the sun. Eratosthenes knew another fact. He knew that a stick stuck in the ground in Alexandria at the same time and the same day at noon, the sun's zenith, on the solstice, the sun cast a shadow that showed it was 7.2 degrees off axis. Now, if you know the circumference of a circle, and you have 2 points on it, all you need to know is the distance between those 2 points, and you can extrapolate the circumference. 360 degrees divided by 7.2 equals 50. I know it's a little bit of a round number, and it makes me suspicious of this story too, but it's a good story, so we'll continue with it. He needed to know the distance between Swenet and Alexandria, which is good because Eratosthenes was good at geography. In fact, he invented the word geography. The road between Swenet and Alexandria was a road of commerce, and commerce needed to know how long it took to get there. It needed to know the exact distance, so he knew very precisely that the distance between the 2 cities was 500 miles. Multiply that times 50, you get 25,000, which is within 1% of the actual diameter of the Earth. He did this 2,200 years ago. Now, we live in an age where multi-billion-dollar pieces of machinery are looking for the Higgs boson. We're discovering particles that may travel faster than the speed of light. And all of these discoveries are made possible by technology that's been developed in the last few decades. But for most of human history, we had to discover these things using our eyes and our ears and our minds. Armand Fizeau was an experimental physicist in Paris. His specialty was actually refining and confirming other people's results. And this might sound like a bit of an also-ran, but in fact this is the soul of science, because there is no such thing as a fact that cannot be independently corroborated. And he was familiar with Galileo's experiments in trying to determine whether or not light had a speed. So Galileo had worked out this really wonderful experiment where he and his assistant had a lamp. Each one was holding a lamp, and Galileo would open his lamp and his assistant would open his lamp. And they got the timing down really good. They just knew their timing. And then they stood at 2 hilltops 2 miles distant. And they did the same thing on the assumption from Galileo that if light had a discernible speed, he'd notice a delay in the light coming back from his assistant's lamp. But light was too fast for Galileo. He was off by several orders of magnitude when he assumed that light was roughly 10 times as fast as the speed of sound. Fizeau was aware of this experiment. He lived in Paris, and he set up 2 experimental stations roughly 5.5 miles distant in Paris. And he solved this problem of Galileo's, and he did it with a really relatively trivial piece of equipment. He did it with one of these. I'm going to put away the clicker for a second because I want to engage your brains in this. Now, this is a toothed wheel. It's got a bunch of notches and it's got a bunch of teeth. This was Fizeau's solution to sending discrete pulses of light. He put a beam behind one of these notches. If I point a beam through this notch at a mirror 5 miles away, that beam is bouncing off the mirror and coming back to me through this notch. But something interesting happens. As he spins the wheel faster, he notices that it seems like a door is starting to close on the light beam that's coming back to his eye. Why is that? It's because the pulse of light, it's not coming back through the same notch. It's actually hitting a tooth. And he spins the wheel fast enough, and he fully occludes the light. And then, based on the distance between the two stations and the speed of his wheel and the number of notches in the wheel, he calculates the speed of light to within 2% of its actual value. And he does this in 1849. This is what really gets me going about science. Whenever I'm having trouble understanding a concept, I go back and I research the people that discovered that concept. I look at the story of how they came to understand it. And what happens when you look at what the discoverers were thinking about when they made their discoveries is you understand that they are not so different from us. We are all bags of meat and water. We all start with the same tools. I love the idea that different branches of science are called fields of study. Most people think of science as a closed black box, and in fact, it is an open field, and we are all explorers. The people that made these discoveries just thought a little bit harder about what they were looking at, and they were a little bit more curious. And their curiosity changed the way people thought about the world, and thus it changed the world. They changed the world, and so can you. Thank you.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal. and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
So I'm here today to encourage you to think about New York City, and not just as one of humanity's greatest achievements, but as home to native wildlife that are subject to a grand evolutionary experiment. So take this forested hillside in northern Manhattan, for example. This is one of the last areas left in the city where there's clean spring water that's still seeping out of the ground. You could drink this out of your hands, you'd be okay. These tiny little areas of seeping water contain huge populations of northern dusky salamanders. These guys were common in the city maybe 60 years ago, but now they're just stuck on this single hillside in a few places in Staten Island. Not only do they suffer the indignity of being stuck on this hillside, but we divided that hillside in two on two different occasions with bridges crossing from the Bronx into Manhattan. But they're still there on either side of the bridges where you see the red arrows, about 180th Street, 167th Street. And my lab has found that if you just take a few segments of DNA from salamanders in those two locations, you can tell which side of the bridge they came from. We built this single piece of infrastructure that's changed their evolutionary history. We can go study these guys, we just go to the hillside, we know where they are, we flip over rocks so we can catch them. There are a lot of other things in New York City, though, that are not that easy to capture, such as this guy, Coyote. We caught him on an automatic camera trap somewhere in an undisclosed location. I'm not allowed to talk about it yet. But they're moving into New York City for the first time. They're very flexible, intelligent animals. This is one of this year's pups checking out one of our cameras. And my colleagues and I are very interested in understanding how they're going to spread through the area, how they're going to survive here, and maybe even thrive. And they're probably coming to a neighborhood near you if they're not already there. So there's some things that are too fast to be caught by hand. We can't pick them up on the cameras. So we actually set out traps all around New York City in the parks. This is one of our most common activities. Here's some of my students and collaborators getting the traps out ready. And this guy we catch in almost every forested area in New York City. This is the white-footed mouse. This is not the mouse you find running around your apartment. This is a native species, been here long before humans, and you find them in forests and meadows. Because they're so common in forested areas in the city, we're using them as a model to understand how species are adapting to urban environments. So if you think back 400 years ago, the 5 boroughs would have been covered in forest and other types of vegetation. This mouse would have been everywhere. Huge populations that showed few genetic differences across the landscape. But if you look at the situation today, they're just stuck in these little islands of forest scattered around the city. Just using 18 short segments of DNA, we can pretty much take a mouse, somebody could give us a mouse, not tell us where it was from, and we could determine what park it came from. That's how different they become. You'll notice in the middle of this colored figure here, there's some mixed up colors. There are a few parks in the city that are still connected to each other with strips of forest, so that the mice can run back and forth and spread their genes so they don't become different. But throughout the city, they're mostly becoming different in the parks. All right, so I'm telling you they're different, but what does that really mean? What's changing about their biology? To answer this question, we're sequencing thousands of genes from our city mice and comparing those to thousands of genes from the country mice, so their ancestors outside of New York City in these big, more wilderness areas. Now, genes are short segments of DNA that code for amino acids. And amino acids are the building blocks of proteins. Now, if a single base pair changes in a gene, you can get a different amino acid, which will then change the shape and structure of the protein. If you change the structure of a protein, you often change something about what it does in the organism. Now, if that change leads to a longer life or more babies for a mouse, something evolutionary biologists call fitness, then that single base pair change will spread quickly in an urban population. So this crazy figure is actually called a Manhattan plot because it kind of looks like a skyline. And each dot represents one gene. And the higher the dot is in the plot, the more different it is between city and country mice. The ones kind of at the tips of the skyscrapers are the most different, especially those above the red line. And these genes encode for things like immune response to disease. So there might be more disease in very dense urban populations. Metabolism, how the mice use energy. And heavy metal tolerance. You guys could probably predict that New York City soils are pretty contaminated with lead and chromium and that sort of thing. And now our hard work is really starting. We're going back into the wilds of New York City parks, following the lives of individual mice and seeing exactly what these genes are doing for them. And I would encourage you guys to try to look at your parks in a new way. I'm not going to be the next Charles Darwin, but one of you guys might be, so just keep your eyes open. Thank you.
Would mathematics exist if people didn't? Since ancient times, mankind has hotly debated whether mathematics was discovered or invented. Did we create mathematical concepts to help us understand the universe around us? Or is math the native language of the universe itself, existing whether we find its truths or not? Are numbers, polygons, and equations truly real, or merely ethereal representations of some theoretical ideal? The independent reality of math has some ancient advocates. The Pythagoreans of 5th century Greece believed numbers were both living entities and universal principles. They called the number 1 the monad, the generator of all other numbers and source of all creation. Numbers were active agents in nature. Plato argued mathematical concepts were concrete and as real as the universe itself, regardless of our knowledge of them. Euclid, the father of geometry, believed nature itself was the physical manifestation of mathematical laws. Others argue that while numbers may or may not exist physically, mathematical statements definitely don't. Their truth values are based on rules that humans created. Mathematics is thus an invented logic exercise, with no existence outside mankind's conscious thought, a language of abstract relationships based on patterns discerned by brains, built to use those patterns to invent useful but artificial order from chaos. One proponent of this sort of idea was Leopold Kronecker, a professor of mathematics in 19th century Germany. His belief is summed up in his famous statement, "God created the natural numbers. All else is the work of man." During mathematician David Hilbert's lifetime, there was a push to establish mathematics as a logical construct. Hilbert attempted to axiomatize all of mathematics, as Euclid had done with geometry. He and others who attempted this saw mathematics as a deeply philosophical game, but a game nonetheless. Henri Poincaré, one of the fathers of non-Euclidean geometry, believed that the existence of non-Euclidean geometry, dealing with the non-flat surfaces of hyperbolic and elliptical curvatures, proved that Euclidean geometry, the long-standing geometry of flat surfaces, was not a universal truth, but rather one outcome of using one particular set of game rules. But in 1960, Nobel Physics laureate Eugene Wigner coined the phrase the unreasonable effectiveness of mathematics, pushing strongly for the idea that mathematics is real and discovered by people. Wigner pointed out that many purely mathematical theories, developed in a vacuum, often with no view towards describing any physical phenomena, have proven decades or even centuries later to be the framework necessary to explain how the universe has been working all along. For instance, the number theory of British mathematician Godfrey Hardy, who had boasted that none of his work would ever be found useful in describing any phenomena in the real world, helped establish cryptography. Another piece of his purely theoretical work became known as the Hardy-Weinberg law in genetics and won a Nobel Prize. And Fibonacci stumbled upon his famous sequence while looking at the growth of an idealized rabbit population. Mankind later found the sequence everywhere in nature, from sunflower seeds and flower petal arrangements to the structure of a pineapple, even the branching of bronchi in the lungs. Or there's the non-Euclidean work of Bernhard Riemann in the 1850s, which Einstein used in the model for general relativity a century later. Here's an even bigger jump. Mathematical knot theory, first developed around 1771 to describe the geometry of position, was used in the late 20th century to explain how DNA unravels itself during the replication process. It may even provide key explanations for string theory. Some of the most influential mathematicians and scientists of all of human history have chimed in on the issue as well, often in surprising ways. So, is mathematics an invention or a discovery? Artificial construct or universal truth? Human product or natural, possibly divine creation? These questions are so deep, the debate often becomes spiritual in nature. The answer might depend on the specific concept being looked at, but it can all feel like a distorted Zen koan. If there's a number of trees in a forest, but no one's there to count them, does that number exist?
Flying through the night, I watch over this world, a silent guardian, a watchful protector, a dark knight.
Okay, fine, so I'm not Batman. I'm just a bat. But like Batman, I'm often misunderstood. People think I'm scary, strange, and dangerous. If they only knew my story, though, I'd be cheered as a hero. When people think of bats, many think of vampires who want to suck their blood. But the truth is that out of over 1,200 bat species, only 3 are vampire bats. Out of these 3, only 1 prefers the blood of mammals. And even these bats mostly feed on cattle. Maybe that still doesn't seem so great, but vampire bats can be a great help to humans. A chemical known as desmoteplase found in vampire bat saliva helps break down blood clots and is being tested by recovering stroke victims. Of the remaining 1,000+ species of bats, about 70% feed on insects. These bats help control the real vampires, mosquitoes, whose nasty bites are not just annoying, but spread diseases like West Nile virus. A single little brown bat can eat 1,000 insects every hour, and a colony of Mexican free-tailed bats can eat several tons of moths in just one night. In the United States alone, bats provide an estimated $3.7 billion worth of free pest control for farmers, which benefits everyone who eats the foods that they grow. Fruit bats, also called megabats because of their large size, are important for the role they play in plant pollination. By traveling between flowers while feeding on nectar and fruits, these bats transport the pollen and seeds that help plants reproduce. In Southeast Asia, for example, the cave nectar bat is the only pollinator of the durian fruit. Other bats pollinate peaches, bananas, and the agave plants that tequila is made from. Without them, many of our food plants would be unable to produce the tasty fruits we enjoy. As heroes of the ecosystem, bats have their own unique utility belts. Bats have been a source of inspiration for the design of flying robots, and even an energy-efficient spy plane, as they are the only mammal capable of true powered flight. Echolocation, a type of biological sonar, is also used by bats as a way to navigate and find prey in the dark. Although there's a common misconception that bats are blind, in truth, all species of bats have sight, and some have even adapted large eyes to see better in dim lighting. Many people worry about getting infected by bats, and like any other animals, bats can carry diseases like rabies. In reality, though, less than half of 1% of all bats carry this virus. That's about the same odds as getting the same result on a coin flip 8 times in a row. The perception that bats are often diseased may come from the fact that sick bats, who may show unusual behavior, emerge during the daytime, or be unable to fly, are more likely to be encountered by people. So a good way to protect yourself is to protect bats as well, keeping them healthy, protecting their habitats, and reducing their risk of transmitting disease. In North America, bats are threatened by a devastating sickness called white nose syndrome. This fungal infection causes bats to wake up while hibernating during the winter. Unable to find food, they expend large amounts of energy and eventually starve to death. White nose syndrome has wiped out entire caves full of bats, with a mortality rate that can exceed 90%. Climate change and habitat destruction also pose serious threats to bat populations. For example, in January 2014, a record heat wave in Australia caused over 100,000 bats to die from heat exhaustion. Some people just want to watch the world burn, and bats all over the world are threatened by damage to the places that we call home, including mangrove swamps, old-growth forests, and of course, bat caves. So even though I'm the hero of the story, I do need to be saved. And now that you know the true story about us bats, you can learn how to protect such heroic animals. Install a properly designed bat box, one of the easiest ways to provide shelter for bats. Discourage the use of pesticides, which can harm bats when we try to feed on the insects you want to get rid of in the first place. Avoid going into caves where you might disturb hibernating bats, and always decontaminate your gear after visiting a cave. If you have unwanted bats living in an attic or barn, contact your local government to safely and humanely relocate us. And if you come across a bat, do not attempt to handle it, but instead call animal control. Batman might want to keep his identity secret, but a great way to help real bats is by continuing to learn about them and spreading the truth that they are real heroes, even if their good deeds are often unseen. You've probably heard that carbon dioxide is warming the Earth. But how does it work? Is it like the glass of a greenhouse? Or like an insulating blanket? Well, not entirely. The answer involves a bit of quantum mechanics. But don't worry, we'll start with a rainbow. If you look closely at sunlight separated through a prism, you'll see dark gaps where bands of color went missing. Where did they go? Before reaching our eyes, different gases absorbed those specific parts of the spectrum. For example, oxygen gas snatched up some of the dark red light, and sodium grabbed 2 bands of yellow. But why do these gases absorb specific colors of light? This is where we enter the quantum realm. Every atom and molecule has a set number of possible energy levels for its electrons. To shift its electrons from the ground state to a higher level, a molecule needs to gain a certain amount of energy. No more, no less. It gets that energy from light, which comes in more energy levels than you could count. Light consists of tiny particles called photons, and the amount of energy in each photon corresponds to its color. Red light has lower energy and longer wavelengths. Purple light has higher energy and shorter wavelengths. Sunlight offers all the photons of the rainbow, so a gas molecule can choose the photons that carry the exact amount of energy needed to shift the molecule to its next energy level. When this match is made, the photon disappears as the molecule gains its energy, and we get a small gap in our rainbow. If a photon carries too much or too little energy, the molecule has no choice but to let it fly past. This is why glass is transparent. The atoms in glass do not pair well with any of the energy levels in visible light, so the photons pass through. So which photons does carbon dioxide prefer? Where is the black line in our rainbow that explains global warming? Well, it's not there. Carbon dioxide doesn't absorb light directly from the sun. It absorbs light from a totally different celestial body, one that doesn't appear to be emitting light at all: Earth. If you're wondering why our planet doesn't seem to be glowing, it's because the Earth doesn't emit visible light. It emits infrared light. The light that our eyes can see, including all of the colors of the rainbow, is just a small part of the larger spectrum of electromagnetic radiation, which includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. It may seem strange to think of these things as light, but there is no fundamental difference between visible light and other electromagnetic radiation. It's the same energy, but at a higher or lower level. In fact, it's a bit presumptuous to define the term visible light by our own limitations. After all, infrared light is visible to snakes, and ultraviolet light is visible to birds. If our eyes were adapted to see light of 1900 megahertz, then a mobile phone would be a flashlight and a cell phone tower would look like a huge lantern. Earth emits infrared radiation because every object with a temperature above absolute zero will emit light. This is called thermal radiation. The hotter an object gets, the higher frequency the light it emits. When you heat a piece of iron, it will emit more and more frequencies of infrared light, and then, at a temperature of around 450 degrees Celsius, its light will reach the visible spectrum. At first, it will look red hot, and with even more heat, it will glow white with all of the frequencies of visible light. This is how traditional light bulbs were designed to work, and why they're so wasteful. 95% of the light they emit is invisible to our eyes. It's wasted as heat. Earth's infrared radiation would escape to space if there weren't greenhouse gas molecules in our atmosphere. Just as oxygen gas prefers the dark red photons, carbon dioxide and other greenhouse gases match with infrared photons. They provide the right amount of energy to shift the gas molecules into their higher energy level. Shortly after a carbon dioxide molecule absorbs an infrared photon, it will fall back to its previous energy level and spit a photon back out in a random direction. Some of that energy then returns to Earth's surface, causing warming. The more carbon dioxide in the atmosphere, the more likely that infrared photons will land back on Earth and change our climate. Think about all the things that need to happen for a human settlement to thrive: obtaining food, building shelter, raising children, and more. There needs to be a way to divide resources, organize major efforts, and distribute labor efficiently. Now imagine having to do this without any sort of planning or higher-level communication. Welcome to the ant colony. Ants have some of the most complex social organization in the animal kingdom, living in structured colonies containing different types of members who perform specific roles. But although this may sound similar to some human societies, this organization doesn't arise from any higher-level decisions, but is part of a biologically programmed cycle. In many species, all the winged males and winged virgin queens from all the nearby colonies in the population each leave from their different nests and meet at a central place to mate, using pheromones to guide each other to a breeding ground. After mating, the males die off, while females try to establish a new colony. The few that are successful settle down in a suitable spot, lose their wings, and begin laying eggs, selectively fertilizing some using stored sperm they've saved up from mating. Fertilized eggs grow into female workers who care for the queen and her eggs, build and defend the colony, and forage for food, while unfertilized eggs grow into males whose only job is to wait until they are ready to leave the nest and reproduce, beginning the cycle again. So how do worker ants decide what to do and when? Well, they don't really. Although they have no methods of intentional communication, individual ants do interact with one another through touch, sound, and chemical signals. These stimuli accomplish many things, from serving as an alarm to other ants if one is killed, to signaling when a queen is nearing the end of her reproductive life. But one of the most impressive collective capabilities of an ant colony is to thoroughly and efficiently explore large areas without any predetermined plan. Most species of ants have little or no sense of sight and can only smell things in their vicinity. Combined with their lack of high-level coordination, this would seem to make them terrible explorers. But there is an amazingly simple way that ants maximize their searching efficiency, by changing their movement patterns based on individual interactions. When two ants meet, they sense each other by touching antennae. If there are many ants in a small area, this will happen more often, causing them to respond by moving in more convoluted, random paths in order to search more thoroughly. But in a larger area with less ants, where such meetings happen less often, they can walk in straight lines to cover more ground. While exploring their environment in this way, an ant may come across any number of things, from threats or enemies to alternate nesting sites. And some species have another capability known as recruitment. When one of these ants happens to find food, it will return with it, marking its path with a chemical scent. Other ants will then follow this pheromone trail, renewing it each time they manage to find food and return. Once the food in that spot is depleted, the ants stop marking their return, the scent dissipates, and ants are no longer attracted to that path. These seemingly crude methods of search and retrieval are in fact so useful that they are applied in computer models to obtain optimal solutions from decentralized elements, working randomly and exchanging simple information. This has many theoretical and practical applications, from solving the famous traveling salesman problem to scheduling computing tasks and optimizing internet searches, to enabling groups of robots to search a minefield or a burning building collectively without any central control. But you can observe these fascinatingly simple yet effective processes directly through some simple experiments by allowing ants to enter empty spaces of various sizes and paying attention to their behavior. Ants may not be able to vote, hold meetings, or even make any plans, but we humans may still be able to learn something from the way that such simple creatures are able to function so effectively in such complex ways.